way that we explore this relationship between mathematical stability and physical stability is going to be through this notion of what we call statical classification. The first of which of those classes is the statically determinate situation. What we're really going to do is we're going to compare the number of unknowns that we have in the system versus the number of equations. It's a very simple, basic mathematical scenario here. So we're going to take a look at, for a typical situation, we might have a number of independent reaction components. Those would be force unknowns. So that's really what we're dealing with here in our modeling is, well, what are the unknown forces in our system? Right? So if we look down here below, we've got a pin support, we've got a roller support, and so for that particular situation, we would have then R would be equal to 2 plus 1 or 3, X and Y at one support and just 1 at the other one. Right? Those would be our number of force unknowns from an external perspective. On the internal perspective, we have these unknown member forces. Now, in a truss, of course, we only have 2 force members. Right? They're either going to be in compression or they're going to be in tension. So that's not the nature of the 2 force. Remember, the 2 forces, if you're in compression, if you know what the force is at one end, you know exactly what the force is at the other end. There's only 2 forces on the free body diagram of the member. Same thing with these tension members, because of course in a truss we have members that are pin connected. The loads are only applied at the joints. So when we do this counting, you have to keep in mind that in our basic truss model, members in the mathematical model go from joint to joint to joint to joint to joint. So in this case, we have 1, 2, 3, 4 members along the bottom chord, 5, 6, 7, 8. Now that we are looking at the top chord, and then 9, 10, 11, 12, 13 for the total number, so M would be equal to 13. Right, so the total number of unknown forces in the system then would be equal to the sum of those 2, and in our example, then that would be, of course, 3 plus the 13 would be equal to a total number of 16 unknowns. In order for us to solve for all of those, we have to have 16 equations. So let's go take a look at that. The equations of which we speak are equilibrium equations that are available to us. And in the case of a truss, we could go look at the free body diagram of the joints. And because of that, again, a basic notion that every single joint where the members are connected are pin connected. So when we draw then the little stubs of the members that come in, then we're not going to have any shear or bending moment associated with those members. We're only going to have compressive forces or tensile forces and any potential reactions and any applied forces that might be happening at that joint. Right? This is, of course, a concurrent force system, and in 2D that means that we've only got 2 available equations of equilibrium for us, sum of forces in the x, sum of forces in the y. Right? Again, in 2D only. So we have 2 equations per joint. So that means, of course, if we have J as our number of joints in the structure, then our number of equations of equilibrium would be then 2 times J. And in our case, then, we have 1, 2, 3, 4, 5, 6, 7, 8 joints. So J equals 8. 2J is 2 times 8. And that's, of course, 16. And notice that in this particular situation here, then, that U is equal to N. And in that particular case, that is what we call a statically determinate system. Right? And that's entirely just about that we have enough equations of static equilibrium to be able to determine all of the unknowns in the system. It's a little more complicated than that in other situations, and that's what we'll look at next.